Now let's look at commonly used continuous distribution. The first one is normal distribution, which everybody is familiar with, and it's a bell-shaped distribution. It's symmetric, goes from minus infinity to plus infinity. Now log normal distribution is like normal, but it has a right side skew. It's good for modeling incomes within a group where you'll find most of them stuck around the middle portion, and then there are just a small group of people way out to the right. So that would be, it's kind of skewed to the right. That would be like a log normal. So log normal shape is something like this, and you can look at the shapes in the distribution. So if you go to define, and then so this is a continuous distribution, so you select continuous, and then you look for log normal. Okay, so and then you set up your mu and sigma. You get the shape of the distribution. Now student t distribution is a kind of normal distribution. Okay, so normal distribution can have any mean and any standard deviation, right? But if the mean is 0 and standard deviation is 1, we call that standard normal. Now student t is like standard normal. It's always mean 0, standard deviation is equal to 1, but it has a standard deviation, well, it has a thicker tail. Okay. So normally t distribution is for when you take x bar minus mu divided by the standard error of x bar, which is sigma or square root of n, you get a student t distribution. So compared to normal distribution, student t will have a thicker tail. Now beta distribution is skewed to the left. Now the thing about beta is beta distribution values range from 0 to 1. Okay, so the x value can only be 0 to 1. So that means it's a good distribution to simulate probabilities, because probabilities are between 0 and 1. So this is a good distribution to simulate probability values. So models the uncertainty of an event, so that must be event, probability of defective or uncertainty of about something happening. And there are two parameters for beta distribution, alpha and beta. Increasing the alpha shifts the curve to the right, so which generates higher values, and increasing value of beta shifts the curve to the left, then you get more probabilities on the smaller side. So these are so here are a couple of examples of alpha and beta reversed, and you see if high alpha, low beta, probabilities will be relatively large. Okay, and the reverse, the probabilities coming out of beta distribution will be relatively small. And when alpha and beta are both the same, you get normal distribution. And of course, the x values can only be from 0 to 1. Now, exponential distribution has a parameter of beta, which is the mean of the distribution, and it is usually paired with Poisson distribution in the discrete case. The Poisson distribution is for a given time slice, how many successes will occur, right? So that's your Poisson. Now, if you look at two successive events, okay, so you're looking at one success, okay, and then the time it takes for the next success. Okay, that time taken, if the number of occurrences is Poisson, then the time taken between successes, the time length, will follow exponential distribution. So you can, if you have in 1 hour, Poisson says, okay, on the average we get 10 events. Average number of events is 10. So that means the average length of time between events will be 6 minutes. Then that becomes the average of exponential distribution. So the parameter beta is the mean of the distribution, so that's what you would use. So again, you can look at beta distribution here. So you have exponential distribution, so you go to define, expand. Okay, so here is beta. You can change the beta distribution. So you want 6 or 10 events in Poisson. So that means 6 minutes. Okay, so here is the length of time it will take for the next event to occur, with 6 minutes being the mean. Yeah. So that's what we saw in our previous discrete file that we were looking at. Okay, with Poisson coming from that, then exponential will be, that would be the mean, and if the probability of success is 0.05, so 1 over that will be the beta value. So there will be 20 minutes between successes, and you get the mean and standard deviation in that way. Okay, and then gamma distribution. Gamma distribution is a special case of exponential distribution. So it's a generalized, not exponential is a special case of gamma. Here, exponential is about the next success, next arrival of an event, whereas gamma is the waiting time for the rth arrival. So you specify, I want to look at the 5th arrival, so 5th failure or 5th breakdown, or whatever the number may be. So that would be a generalized exponential or gamma distribution. And the number of arrivals, like in the case of exponential, number of arrivals follows Poisson distribution. In gamma also, the individual arrivals will follow Poisson distribution, and the time between one arrival and a given number of arrivals will be gamma distribution. So it has a minimum of 0 on the right hand side is skewed to the right. And flexible, it's a very flexible distribution, and it is used for a variety of applications. And again, it has 2 parameters, alpha and beta, and these are called, alpha is called the shape parameter. So what kind of shape? Whether it's going to be skewed to the right like that, or has a hump and then a skew, or it has just, in the exponential case, the shape will be like that. There won't be a hump. It'll be declining monotonically like this. Now, scale parameter is this, how spread out the values are. So here are 3 different. So for alpha is 10, shape is the kind of normal looking, and then so beta of 1 is very small scale, beta of 3 has a larger scale, and beta of 5 is even much larger scale. So these are the 2 parameters, and the shape and the size, and again you try to fit as close to, if your process is going to give values in this fashion, then you will use gamma distribution. So here is another, with beta being the same, okay, alpha 1, 3, 5, where the shape changes. With beta, the scale being the same, you change alpha, the shape changes.